In 2015, in a short paper in the astrophysical journal Letters that almost nobody outside of exoplanet astronomy noticed at the time, two astronomers at the University of Warwick named Tom Louden and Peter Wheatley used a spectrograph attached to the Very Large Telescope in northern Chile to do something that had never been done before. They measured for the first time in human history the speed of the wind on a planet outside our own solar system. The planet is called HD 18973b. It is a hot Jupiter, slightly larger than our own Jupiter, 64 light-years from Earth in a small dim constellation called Vulpecula, the little fox. The wind speed they measured when they finished the analysis was about 5,400 miles per hour. Not the strongest hurricane on Earth, which is around 190. Not the strongest jet stream ever recorded in our own atmosphere, which is around 300, 5,400. Mach 7. And here is what almost nobody outside of exoplanet astronomy has ever sat with. The wind on this planet is not just fast. The wind is carrying glass, tiny droplets of vaporized silicate condensed in the upper atmosphere, blowing sideways across the entire day side of the planet in winds that move parallel to the surface at 7 times the speed of sound. It rains glass on this planet. It blows glass. The whole sky, when you photograph it carefully, is a deep cobalt-blue haze of small silica particles suspended in a permanent atmospheric gale that has been blowing almost certainly for as long as the planet has existed. If you find that as fascinating as I do, hit subscribe. Pour yourself something warm, get comfortable, and settle in. Because tonight we are going to walk slowly through the strange and quietly beautiful story of a world made of cobalt-blue weather, of clouds that fall as broken glass, of winds at 7 times sound, and of how, from 64 light-years away, on a quiet evening at a mountaintop observatory in northern Chile, a small team finally heard the gale. Now, let's ease into it. Part 1. The Little Blue Planet. HD 18973b was found in 2005 by a French team led by an astronomer named François Bouchy at the Observatoire de Haute-Provence in southern France. The instrument they used was a spectrograph called LED, an older instrument by the standards of the time, but a precise one. LED worked by measuring the velocity of a star toward and away from Earth very precisely by looking at how the star's spectral lines were shifted in wavelength. If a star has a planet, the planet's gravity pulls the star very slightly in a small wobble around the system's center of mass. The wobble shows up in the spectrum as a tiny periodic Doppler shift. LED could measure these shifts to a precision of a few meters per second. It was, in 2005, one of the most sensitive instruments in the world for finding planets by this technique. When LED was pointed at a yellow-orange star designated HD 18973 in the constellation Vulpecula, 64 light-years from Earth, it found a wobble. The wobble had a period of 2¼ days. The shape of the wobble suggested a planet about as massive as Jupiter, in a tight, close-in orbit. The team announced the discovery, and within months, follow-up observations using the transit method by a different team confirmed that the planet did indeed pass in front of its star, dimming it by a few percent every 2¼ days. The planet was real. It was named by the convention of the field, HD 1897733b, the little b indicating that it was the first planet to be found around the star HD 1897733. There is a small detail about the discovery worth mentioning because it tells you something about how the field worked at the time. The Bouchy paper, when it was published in October of 2005, was not on the cover of any major journal. It was a routine announcement in astronomy and astrophysics of one more transiting hot Jupiter found by an established group using an established instrument. The field, by 2005, had been finding planets at a steady rate for a decade. Each new one was in the trade press, a few paragraphs. None of them individually was treated as world-changing. The accumulation, year by year, was what mattered. The individual papers were quiet. The catalogue, when you stood back from it, was filling in. What set HD 189733b apart in the years that followed was none of the things that were known at the time of discovery. It was the proximity which made follow-up easy. It was the brightness of the host star which made spectroscopy possible. It was the geometry of the orbit which made transits clean and repeatable. It was, in some sense, the lucky combination of features that made the planet a good target for almost every technique that anyone wanted to try. And so, as the techniques developed over the following 20 years, HD 189733b kept being chosen. Each new instrument, when it came online, looked at HD 189733b first. The accumulated data by the early 2020s was richer than for any other exoplanet anywhere. There is a cumulative effect in this kind of work that goes beyond any individual paper. When a single object is studied by many different teams with many different instruments over many different years, the resulting body of literature becomes a kind of common reference. Researchers who are interested in a related topic, but who do not have time or resources to study it themselves, can read the HD 189733b papers and use the results as inputs to their own work. Theoreticians can use the constraints from this single planet to test their models. Instrument designers can use the planet as a benchmark to validate new techniques. The whole field, in some sense, gets the benefit of the work that one planet's worth of intensive study has produced. HD 189733b in this sense has been a public good. Its proximity made it cheap to study. Its thorough characterization has, in turn, made it cheap to use as a reference. The whole field is, very quietly, more efficient because of it. For our purposes, the most important fact about HD 189733b is its proximity. 64 light-years by the standards of cosmic distances is very close. Not close enough to visit, not close enough to communicate with on any reasonable timescale, but close enough that the planet is, by a comfortable margin, one of the brightest exoplanet targets in the sky. The host star, HD 189733, has a magnitude of about 7 3/4. That is just below the threshold of unaided eye visibility, but a small backyard telescope, or even a good pair of binoculars under dark skies, can see it. Most of the people listening to this story tonight could, in principle, find HD 189733 in their own back garden, given a clear night and the right star chart. The planet itself, of course, is not visible. The planet is much too small and much too dim to ever be seen from Earth. But the star is right there. That brightness has consequences. Because HD 189733 is bright, the transits are easy to measure. The wobble is easy to measure. The atmospheric chemistry is, by exoplanet standards, easy to measure. Almost every technique that astronomers have developed for studying exoplanet atmospheres has been tried, at one point or another, on HD 189733b. It is, by some margin, the most thoroughly studied exoplanet in the catalogue. There are more papers about HD 189733b's atmosphere than about almost any other single object in modern astronomy. And the picture that has emerged over 20 years of observation is the picture of a world that, in almost every respect, is unlike anything we have in our own solar system. The first thing we learned by careful follow-up using a range of instruments was the basics. The planet has about 1/10 times the mass of Jupiter and about 1/10 times its radius. It is, in size, a Jupiter twin. The orbit is 2¼ days, much shorter than any planet in our own system. Mercury, which is the fastest of our planets, takes 88 days to circle the Sun. HD 189733b takes 2¼ Its orbital distance is about 3.5 million miles from its star, which is, very roughly, 25 times closer than Mercury is to our Sun. At that distance, the day side of the planet is heated to a temperature of roughly 1200 degrees Celsius, hot enough to melt aluminium, hot enough to glow faintly in the dark with the same kind of dull red-orange glow that a piece of iron has when it has been in a forge for half an hour. But the planet does not glow visibly to us, of course. From 64 light-years away, even an entire planet at 1200 degrees is, in its emission, lost in the glare of its star. We do not see the planet directly. We see instead what its passage in front of its star every 2¼ days does to the spectrum we receive. And what that spectrum has been telling us for the better part of 20 years is that this small hot world in its little corner of Vulpecula is one of the strangest weather systems we have ever measured. Part 2. How we found out it was blue. There is a particular result from 2013 that put HD 189733b in the public imagination in a way that almost no other exoplanet before or since has been put. The result was a measurement of the planet's colour. Up until then, the colours of other planets, in any literal sense, had been the subject of theoretical models and not direct measurement. We knew the colours of the planets in our own solar system because we have been to them, or at least photographed them up close. Mars is rust orange because of iron oxide on its surface. Jupiter is striped tan and cream because of ammonia ice clouds at different depths. Neptune is a deep blue because of methane absorbing the red end of the spectrum. We knew these things by direct imaging. For exoplanets 64 light-years and beyond, no such direct imaging was or is currently possible. We cannot photograph HD 189733b. We can barely separate its light from its stars at all. To know what colour the planet was, you needed a more clever technique. The technique that worked, in the end, was a Hubble Space Telescope observation that watched the system as the planet passed behind its star, from our point of view, on what astronomers call the secondary eclipse. During the secondary eclipse, the planet is hidden behind the star. The total light from the system drops, very slightly, by exactly the amount that the planet had been contributing. By comparing the spectrum of the system before and during the secondary eclipse, you can, in principle, isolate the planet's own light. And by looking at how the planet's contribution differs across different wavelengths, you can determine its colour. In 2013, a team led by an astronomer named Tom Evans at the University of Oxford did exactly that, using Hubble's STIS instrument. They measured the secondary eclipse depth at multiple wavelengths across the visible spectrum. The depth was significantly larger in the blue than in the red, which meant that the planet, when illuminated by its star, was reflecting much more blue light than red light, which meant, when you accounted for everything else, that HD 189733b's atmosphere, when you stand back and look at it, is a deep, saturated cobalt-blue. The colour is not, importantly, the same kind of blue that Earth is. Earth looks blue from space because of the oceans, and because of the way the atmosphere scatters short wavelength sunlight. HD 18973b has no oceans. The blue of HD 18973b is a different kind of blue. It is the blue of small particles in the upper atmosphere scattering blue light back towards space, in a process very similar to the one that makes Earth's sky look blue. But on Earth, the scatterers are nitrogen and oxygen molecules. On HD 18973b, they are something heavier, something denser, something that on a planet at 1200 degrees can exist in the upper atmosphere only as a fine droplet of vaporized mineral. The scatterers the team's modelling showed were almost certainly silicate particles, tiny droplets of liquid glass suspended in the air, condensed out of vaporized rock. The blue colour, when they pinned down the chemistry, was the colour of glass clouds. The whole sky of HD 18973b, when you take a picture of it from far enough away to see it as a disk, is a swimming pool of suspended molten glass, cobalt-blue from horizon to horizon, the way the surface of a calm sea looks when the sun is overhead. Let me sit with that for a moment. We measured the colour of a planet 64 light-years away. The colour we got was the colour of glass. The colour result, when it was announced in 2013, was one of those small moments in modern astronomy where the technical detail of the work lined up almost perfectly with the popular imagination. People understand colour. People understand that planets in our own solar system have colours. The idea that you could measure the colour of a planet 64 light-years away and that the colour turned out to be a specific, recognisable shade made the result accessible in a way that almost no exoplanet result before it had been. The press coverage that summer was unusual for the field. The Hubble press office released an artist's impression of the planet, rendered in deep cobalt-blue, with a yellow-orange star in the background, and the image was reprinted in dozens of publications around the world. The planet, briefly, became one of the most recognizable exoplanets in popular culture. What is sometimes lost in the press coverage is how careful the underlying measurement actually was. Hubble's STE instrument in the configuration the team used was being asked to detect a change in stellar brightness of less than 1 part in 10,000 at specific wavelengths over a specific time interval against a background of stellar variability and instrumental noise. The team needed to combine many secondary eclipse observations with very careful calibration before the colour signal rose above the noise floor. The blue, when it appeared statistically. It was not a single observation that gave the result, it was the accumulation of many processed together that allowed the colour to be pinned down. That is, in many ways, the texture of all of this work. The big findings, the ones that make the headlines, are the result of small statistical accumulations. No single transit gives you the colour of a planet. No single observation gives you the wind speed. No single measurement gives you the chemistry. The findings emerge slowly from many observations processed together until the noise averages out and the signal becomes clear. The patience required is, by the standards of most modern professions, unusual. The reward, when it comes, is rare and quiet and worth waiting for. Part 3. What is actually in the air? Even before the colour result, we knew quite a lot about what HD 1897333b's atmosphere contained. The list of detected molecules by 2015 was long enough to make the planet a kind of standard reference object for atmospheric chemistry of hot Jupiters. The list, in rough chronological order, was as follows. Water vapour was detected in 2007 by a team led by an astronomer named Giovanna Tinetti at University College London using the Hubble Space Telescope's NICMOS infrared camera. The signal was small, just a few parts per thousand in the depth of the transit at infrared wavelengths, but it was robust. The atmosphere of HD 189733b contains water, hot water. The water is in the form of high-temperature vapor, mixed with the planet's hydrogen and helium, doing whatever chemistry hot water does in a hydrogen atmosphere at thousands of degrees. But it is there. Methane was detected in 2008 by a team led by Mark Swain at NASA's Jet Propulsion Laboratory, again using Hubble's NICMOS instrument in a different infrared band where methane has a strong absorption line. The methane signal, when it was confirmed, made HD 19733b the first exoplanet anywhere on which methane had ever been detected. That was, briefly, a small media event. Methane on exoplanets, for various reasons, has long been considered a possible biosignature, although, on a hot Jupiter at 1200 degrees, the methane is almost certainly produced by entirely abiotic chemistry and is not a sign of life. Still, the molecule was there. The same molecule that exists in the atmospheres of Saturn and Jupiter and Uranus and Neptune, in our own solar system, present in detectable quantities on a planet 64 light-years away. Sodium was detected slightly later in the visible part of the spectrum in the wings of the famous sodium D line. Sodium, which is what gives ordinary table salt its yellow color when you sprinkle it into a flame, has a very strong absorption line at around 589 nanometers. The Doppler shift of that line in the planet's atmosphere as it passes in front of its star is the measurement we will come back to in a few minutes, because it is the measurement that gave us the wind speed. Carbon monoxide was detected in 2010 from ground-based high-resolution spectroscopy. The carbon monoxide is a major fraction of the atmosphere by some estimates. At the temperatures involved, the chemistry tends to favor carbon being locked up in carbon monoxide rather than in carbon dioxide or methane, although all three exist. Helium was detected in 2018 by a team using the Hubble Space Telescope's Wide Field Camera 3 to observe the helium absorption line at 1.08 micrometers in the near infrared. The helium signal, like the others, was small, but it was robust. The atmosphere of HD 189733b contains helium in proportions consistent with the cosmic abundance, and the helium is being slowly stripped from the planet by the same processes that strip the hydrogen. The helium detection when it came made HD 189733b one of the first planets for which this particular line had been observed. The technique has since been extended to many other systems, and helium detection in exoplanet atmospheres is now a standard part of the toolkit. The original detection on this planet was the first. Each of these detections, taken individually, is a small advance. Each of them has its own paper, its own team, its own follow-up controversies, its own technical refinements. Taken together, they amount to one of the more thorough atmospheric characterizations of any planet that human beings have ever performed. By the time of this telling, we know HD 189733b's atmosphere better than we know the atmosphere of Mars in some respects, because the techniques used to measure it integrate over much longer baselines than the spacecraft observations of Mars do, and because the chemistry of HD 189733b, while extreme, is in some ways simpler than the chemistry of a planet with surface processes and seasonal variability. Atmospheric escape was confirmed in 2011 by a team led by an astronomer named Alain Lecavalier des Étangs at the Institut d'Astrophysique de Paris using Hubble's ultraviolet spectrograph. They observed that, during transit, the planet appeared larger in ultraviolet than in visible light by a substantial amount. The interpretation then and now is that the planet has an extended hydrogen halo around it, and that the halo is being slowly stripped by the ultraviolet flux of the star. The planet is, very slowly, losing atmosphere to space. Not at the dramatic rate of WASP-12b, which we will come back to, but at a measurable rate. The atmosphere is leaking. Iron, magnesium, and several other heavier elements have been tentatively detected in subsequent observations, particularly in ultraviolet spectra, where the absorption lines of these elements show up against the continuum of the star's light. The detections of these heavy elements, when they were announced, made HD 189733b one of the first exoplanets known to have a chemistry that included a substantial fraction of metallic species in its upper atmosphere. The metals are vaporized by the heat of the star, lifted by atmospheric circulation, and detected in the line absorption of the spectrum during transit. Each metal has its own characteristic wavelength signature, and the detection of one metal makes the search for others more straightforward. The interpretation is that, at the very high temperatures of the day side, even some of the heavier metals are vaporized into the upper atmosphere, where they participate in the chemistry of the cloud layers. And, completing the picture, the silicate clouds, the blue droplets, that give the planet its colour. These have not been directly detected as a chemical species in the sense that the absorption lines of pure silica have not been picked out of the spectrum. They have been inferred very robustly from the colour and the polarization of the planet's reflected light, and from the absence of certain absorption features that should be present if there were no clouds, and from the presence of others that fit cloud models very well. The silicate composition, when you fit all the data, is the simplest explanation. The planet is making clouds out of vaporized mineral condensed in the cooler parts of its upper atmosphere, drifting in wind. The drifting, of course, is the part of the story we have not yet fully introduced. The drifting turns out to be the most extreme weather pattern ever measured anywhere in the universe. Part 4. The Doppler measurement. To understand how Tom Louden and Peter Wheatley in 2015 measured the wind speed on HD 189733b, you have to understand a feature of physics that nobody can avoid noticing once they know how to look for it. Light, when it is moving toward you, gets bluer. Light, when it is moving away, gets redder. The amount of blue shift, or redshift, depends on the speed of the source. This is the same effect that makes the pitch of an ambulance siren rise as it approaches and fall as it passes. For visible light, the effect is small unless the source is moving very fast, but for a sensitive enough instrument, even modest velocities can be measured by comparing the wavelengths at which familiar absorption lines appear in the spectrum. When HD 189733b passes in front of its star, light from the star passes through the planet's atmosphere and is absorbed at very specific wavelengths corresponding to the elements present. The sodium D line in particular is one of the easiest absorption lines in the planet's atmosphere to find because it is sharp, isolated, and very strong. By measuring the exact wavelength at which the sodium absorption appears, during transit you can in principle determine whether the absorbing sodium is moving toward you, away from you, or sitting still. Now here is the clever part. Because the planet is rotating and because tidal locking has fixed the planet's day side toward its star and its night side away, there is a permanent atmospheric flow from the day side to the night side. The day side is much hotter than the night side by perhaps 400 or 500 degrees, and the air, very simply, is pushed by the temperature gradient from hot to cold. The pushing is the wind. From a certain viewing angle during the transit, the planet's leading edge is moving toward you, and the trailing edge is moving away, and the wind itself, depending on which side of the planet you are looking at, is either adding to that motion or subtracting from it. The sodium absorption, when you look at it carefully, splits very slightly into a blue shifted component and a red shifted component. The split is a direct measurement of how fast the wind is blowing. Louden and Wheatley, using the high-accuracy radial velocity planet searcher northern instrument called HARPS North on the Telescopio Nazionale Galileo at the Observatorio del Roque de los Muchachos in the Canary Islands, did exactly this measurement. They observed transits of HD 189733b. They isolated the sodium D line absorption. They measured the splitting. And the number that came out after the analysis was a wind speed of about 5,400 miles per hour, blowing from the day side to the night side, across the equator of the planet, at the upper atmospheric level where the sodium lives. 5,400 miles per hour, Mach 7, about twice the speed of a rifle bullet, about 25 times the speed of any wind ever recorded on Earth. Sustained, the team's models suggested, more or less continuously, for as long as the planet has been a tidally locked hot Jupiter, which is almost certainly longer than the entire history of life on our own planet. Let me sit with that for a moment. The wind has been blowing on this planet on the same side, in the same direction, at roughly the same speed, for billions of years. There is a small piece of physics worth pausing on here, because it is the kind of thing that becomes more remarkable the longer you sit with it. The technique that Louden and Wheatley used, the measurement of an absorption line's Doppler split during transit, depends on the planet's rotation and the wind's circulation conspiring to produce a measurable signal. The planet rotates slowly, with a period equal to its orbit, which is 2¼ days. That rotation on its own would not produce a wind. The wind exists because of the day-night temperature gradient, not because of the rotation. But the rotation does carry the wind around in the planet's reference frame, and the result, in the spectrum we measure, is a particular shape. When you observe the planet during the first half of its transit, the leading limb of the planet is moving toward you at a few kilometers per second due to the orbital motion. The trailing limb is moving away from you at the same speed. If the atmosphere was stationary in the planet's reference frame, the absorption line would be smeared symmetrically by these two motions. But the wind is not stationary. The wind is blowing from the day side to the night side, parallel to the equator. On one side of the planet, the wind motion adds to the orbital motion. On the other side, it subtracts. The result is an asymmetric absorption line. The line, when you look at it carefully, is shifted slightly to the blue, on average, during transit. The amount of the shift is the wind speed. That kind of measurement, when you describe it carefully, sounds almost impossible. You are extracting from a small wavelength shift in a single absorption line the speed of an atmospheric jet on a planet 64 light-years away. The signal is in the 3rd or 4th decimal place of the wavelength of light. The instrument has to be stable to better than a meter per second over the duration of the transit. The systematics have to be controlled with care that most fields would consider obsessive. And yet, when you do the work properly, with sufficient patience, the answer comes out clean: 5,400 miles per hour, repeatable across multiple transits, consistent with theoretical models, confirmed since the original measurement by other groups using other instruments. The result is real. The wind is real. The number is real. Here is the part I find most quietly remarkable. The wind has been blowing in the same direction at the same speed since long before anybody on Earth could measure it. The information was always coming. The starlight was always being modulated by the wind, every transit, every 2¼ days since the planet first formed. We just did not have the instruments to read what the starlight was telling us. Now, in our generation, the instruments exist. The reading is, in human terms, brand new. The wind is, by every measurement, very old. Part 5. Here is where it gets strange. Here is where the story shifts, from the chemistry of detection to the picture of what is actually happening on the planet itself. Because once you know the colour and the chemistry and the wind, the picture you can construct of HD 189733b is not the picture of a planet in any of the senses that the word usually means. It is the picture of a sustained atmospheric event the size of Jupiter, going on at the scale of a small star, lasting for the lifetime of an entire system, in which almost everything you would normally associate with a world is replaced by something more transient. There is no surface. The planet, like Jupiter, is a gas giant, with no rocky crust, no oceans, no continents. The interior is a slow gradient from hot, dense gas to ever hotter, denser gas, all the way down to a hypothetical core of heavy elements that may or may not be there, depending on whose model you trust. None of that is what we are talking about when we say the weather. The weather is in the upper atmosphere, the outermost few 100 kilometers of gas, where the pressure is low enough and the temperatures are right for the silicate clouds to condense. That outermost layer, which is what you would see if you flew up to the planet in a hypothetical spacecraft, is the entire visible identity of the planet. There is no day and night cycle. The planet is tidally locked. One side permanently faces the star, the other permanently faces away. The day side is at 1200 degrees Celsius, glowing dull red in its own thermal emission. The night side is much cooler, perhaps 800 degrees, possibly lower, depending on how efficiently the wind transports heat. The terminator, the line between day and night, is a permanent twilight band, where the temperature gradient drives the strongest winds. The wind blows from the day side to the night side in a permanent equatorial jet. The jet is not, strictly speaking, sideways from the perspective of the planet's gravity, which is straight down. The jet is sideways from the perspective of standing on a hypothetical surface, looking horizontally. There is, in the picture, no down to gravitate toward, in any conventional sense. But if you imagine yourself drifting somewhere in the upper atmosphere, at the level where the silicate clouds form, the wind is carrying you, at the speed of 7 times sound, across the planet, from the hot side to the cool side, on a journey that takes a few hours each way, and the wind carries the clouds with it. The silicate droplets, suspended in the upper atmosphere, are moved by the wind in the same way the wind moves any small particle. The clouds are not stationary, they are not localized, they are, on this planet, the wind. The whole sky is moving all the time at extreme speed in a single direction. And because the wind is moving so fast and the temperature is changing so quickly across the day-night terminator, the clouds are continuously condensing and evaporating. On the cool night side, the temperature is low enough that silicate vapor condenses into droplets. The droplets fall in the planet's gravity. The wind blows them, faster than they can fall, around toward the day side. On the hot day side, the temperature is high enough that the droplets evaporate again, releasing the silicate back into the atmosphere as vapor. The vapor rises, mixes, gets blown back to the night side, condenses into droplets again. The cycle in steady state runs continuously all over the planet, every minute, every hour, every year, for the entire age of the system. The rain in this picture is not a passing phenomenon. The rain is a feature of the atmosphere. The glass in the air is not a curiosity. The glass is the air. Part 6. Why glass condenses out of the atmosphere. To understand why glass forms in the upper atmosphere of HD 189733b, you have to understand a piece of chemistry that, on Earth, never gets a chance to be relevant, because it requires temperatures and pressures that no surface on our own planet is ever subjected to. Silicate is, in its broadest definition, any compound containing silicon and oxygen. The crust of the Earth is about 90% silicate. The rocks under your feet, the sand on a beach, the glass in your window, the ceramic of a coffee cup, the dust on the surface of the moon are all silicate compounds in different arrangements. Silicate is, in the universe, one of the most abundant forms of matter. It is the dominant material of the rocky planets in our own system, and it is, in vaporized form, present in the atmospheres of stars, including our own sun. At room temperature, silicate is a solid. To turn silicate into a vapor, you need to heat it to about 1700 degrees Celsius. At 1700 degrees, silicate boils. The boiling is not, normally, a phenomenon of any planet's surface in our own solar system. Earth's hottest natural environments, the cores of active volcanoes, reach about 1300 degrees. Venus's surface is at about 450. Mercury's day-side high is at about 430. Nowhere in our solar system, except in the deep interiors of the gas giants, does silicate ever vaporize. On HD 189733b, the day side, at about 1200 degrees, is just below the silicate boiling point. The hottest spots near the substellar point, where the star is permanently overhead, may reach the boiling point or exceed it. At those temperatures, silicate exists as a vapor, mixed with the planet's hydrogen and helium and other gases. The vapor rises in the warm upward currents of the day-side atmosphere. It mixes laterally, blown by the wind, toward the cooler day-night terminator. As it crosses the terminator, the local temperature drops below the silicate boiling point, and the silicate begins to condense. It does not condense into solid grains in the way water vapor condenses into ice. It condenses into liquid droplets, the same way water condenses into clouds in our own atmosphere, except that the droplets are made of liquid glass. The droplets, at the temperatures and pressures of HD 189733b's upper atmosphere, are extremely small. Modelling work by the German astrochemist Christian Helling at the University of St Andrews suggested that the droplets are typically a fraction of a micrometer across, smaller than the wavelength of visible light. That size matters because particles of that size scatter blue light much more efficiently than red light by a process called Rayleigh scattering. It is the same process that makes Earth's sky blue. On Earth, the scatterers are nitrogen and oxygen molecules. On HD 189733b, they are tiny silica droplets. The result is the same in both cases. Blue light scatters. The atmosphere appears blue to anyone looking at it from outside. The colour of HD 189733b, in other words, is not a coincidence. The colour is a direct consequence of the chemistry of silicate at the planet's temperature and of the physics of light scattering off small particles. The blue is the chemistry made visible. If you took the silicate clouds away, the planet would not be blue. It would be a duller, greyer, redder colour, dominated by the absorption of sodium and potassium in the upper atmosphere. The blue is, very specifically, the signature of the glass. Helling's modelling work, taken together with subsequent papers by other groups, painted a more detailed picture of how the cloud system actually operates. The clouds are not, in any sense, uniform. There are layers at different altitudes where different chemistries dominate. At the deepest cloud layer, somewhere around 100 bars of pressure, the dominant condensate is iron. Tiny droplets of liquid iron suspended in the atmosphere, the same way water condenses on Earth. Above the iron layer, somewhere around 10 bars, the dominant condensate is silicate, in the various forms we have been talking about. Above the silicate, at lower pressures and lower temperatures, lighter materials condense, including various salts and possibly even simple organic compounds, although these are at the edge of what current models can predict. The whole atmosphere, in other words, is a stack of cloud decks, each at its own altitude, each made of a different mineral, each contributing its own absorption and scattering signatures to the spectrum we measure. The blue colour, when we measure it, is the topmost layer of this stack, the silicate haze. The deeper layers are hidden from view in the visible part of the spectrum, but in some infrared bands you can see hints of them. The full picture is one of the more extraordinary atmospheres in the catalogue, not because any one feature is unique, but because the combination on this one specific planet has been characterized in such detail. Here is the part that almost no one outside the field talks about. The cloud chemistry of hot Jupiters, when it works the way HD 189733b's seems to work, is doing something that has no direct equivalent in our own solar system. The clouds of Earth are made of water, the clouds of Jupiter are made of ammonia, ice, the clouds of Saturn are also ammonia. The clouds of Neptune and Uranus are largely methane and hydrogen sulfide. None of these clouds are made of vaporised mineral. None of these atmospheres run hot enough for silicate to be a vapour. The mineralogical clouds of hot Jupiters are, in our local cosmic neighbourhood, found nowhere else. To see this kind of weather, you have to look very far afield. HD 189733b is, in this sense, the closest example of a phenomenon that requires an entire other star system to host. Part 7. The shape of a wind on a tidally locked world. There is a feature of the wind on HD 189733b that I want to spend a moment on because it is one of those small physical curiosities that, the first time you encounter it, sounds absurd, and the second time you encounter it, makes complete sense. The wind on a tidally locked planet is permanent. It does not start. It does not stop. It does not gust. It does not ease at night, because there is no night. It does not pause at dawn, because there is no dawn. It is, in steady state, a continuous flow from the day side to the night side, driven by the temperature difference between the two sides, and balanced by the Coriolis effect from the planet's rotation. The Coriolis effect, on Earth, is what gives our weather systems their large-scale patterns. Hurricanes spin in one direction in the northern hemisphere, and the other direction in the southern, because of the way the rotation of the Earth deflects moving air. On Earth, the Coriolis force is significant on scales of hundreds of kilometres or larger. On HD 189733b, the same effect operates, but the rotation is slower because the planet is tidally locked and the resulting wind pattern is different. Atmospheric circulation models, which have been done in detail for HD 189733b by several groups, including a team at the University of Arizona led by Adam Schoeman, predict a single broad equatorial jet, blowing eastward, across the entire day side, into the night side, and back around again. The jet is not symmetric. The hottest spot on the planet where the temperature is highest and the upward convection is strongest is not directly under the star. It is offset slightly in the direction of the wind. By the time the warmest air rises, the rotation of the planet has carried it a little way past the point where the most energy is being deposited. This offset is small, but it is measurable. It was measured, in fact, in 2007 by a team led by an astronomer named Heather Knudsen at Caltech using the Spitzer Space Telescope. They observed the planet over the course of a full orbit, mapping how the infrared brightness changed as different sides faced toward Earth. The result was the first weather map of any planet outside our own solar system. The map showed a hot spot slightly displaced from the substellar point in the direction the wind was blowing. It was, in 2007, a small revolution. We had measured the location of weather on a planet 64 light-years away. The Knudsen result, more than almost any other, established that exoplanet meteorology was a real and tractable scientific subject. Before then, exoplanet atmospheres were, in the language of physics, point sources. We knew their composition, their temperature, their broad properties. After Knudsen, exoplanet atmospheres had structure. They had hot spots. They had wind. They had the kind of detail that only a real, three-dimensional, dynamic system has. The planet went in a single paper from a small dot in a catalogue to a place with a weather system. The wind speed, when Louden and Wheatley measured it directly 8 years later, fit into the Knudsen picture beautifully. The speed, the direction, the vertical structure all matched the predictions. The picture was self-consistent. The atmosphere of HD 189733b is in a steady-state circulation pattern, with a single broad eastward equatorial jet carrying silicate droplets from the day side to the night side at 5,400 miles per hour in a flow that has been ongoing for billions of years. I am not saying it is the only kind of weather possible on a hot Jupiter. I am not saying every tidally locked planet has the same circulation. I'm not saying we have in this one measurement exhausted the meteorology of these worlds. What I'm saying is something quieter than that. What I'm saying is that, for at least one planet 64 light-years away, we have measured the weather in detail with multiple instruments over more than a decade, and the picture that has emerged is consistent. The planet has weather. The weather is extreme. The weather is permanent. The weather, in a real sense, is the planet. Part 8. The atmosphere is leaking. There is one more feature of HD 189733b's atmosphere that we have not yet covered, which is that slowly it is leaving. The first hint of atmospheric loss came in 2010 from observations by Le Cavelier des Étangs and his collaborators using Hubble's COS spectrograph in the ultraviolet. They watched the system through several transits, looking at the depth of the transit, at the wavelength of the Lyman alpha line, which is the strongest line of atomic hydrogen in the ultraviolet. If the planet has an extended hydrogen halo, the halo will absorb Lyman alpha photons during transit, and the transit at that wavelength will appear deeper than the transit in visible light. The ratio of the two transits tells you very directly how big the hydrogen halo is. For HD 189733b, the result was a clear positive detection. The planet's UV transit was substantially deeper than its visible transit. The hydrogen halo, when modelled, extended to roughly the size of the planet's Roche lobe, the boundary beyond which the planet's gravity can no longer hold material against the pull of the star. Material reaching that boundary, by definition, is being stripped. The atmosphere, in other words, is escaping. The mass loss rate when the team did the calculation was somewhere around 100 million kilograms per second. That number, on its face, is enormous. 100 million kilograms is the mass of a small mountain. The planet, every second, is losing the mass of a small mountain to the star. Over the course of a year, that adds up to about 3 trillion tons. Over the course of 1 billion years, it is about 3,000 quadrillion tons. Substantial fractions of the planet's atmosphere, in other words, are being lost on cosmic timescales. Here is the part where you have to be careful with your scaling, though. 100 million kilograms per second sounds like an enormous amount, until you realize that the planet's total mass is somewhere around 2 times 10 to the 27th kilograms. The mass loss rate, expressed as a fraction of the planet's mass per year, is something like 10 to the minus 13, 1/10 trillionth of the planet every year. At that rate, the planet would last, in principle, 10,000 billion years before being entirely lost to space, which is, by a wide margin, longer than the current age of the universe. Of course, the rate is not constant. As the atmosphere thins, as the orbit evolves, as the star ages, the loss rate will change. But the basic point is that HD 189733b's mass loss, while measurable, is not catastrophic on any reasonable timescale. The planet is not falling apart. The planet is, on its own slow clock, evolving. And the evolution is happening at a pace that is far slower than the planet's likely lifetime against the eventual death of its star. That distinction between WASP-12b's catastrophic 3 million year decay and HD 189733b's leisurely multi-billion year leak is one of the more important contrasts in modern hot Jupiter science. The two planets, on the surface, look similar. Both are gas giants, both are close to their stars, both have extreme atmospheres, but the orbital geometry of WASP-12b puts it inside the regime of catastrophic tidal disruption, while HD 189733b sits comfortably outside that regime. The difference is not in the kind of planet. The difference is in the proximity to the destruction threshold. But, and here is where the comparison with WASP-12b becomes useful, HD 189733b is much further from the brink than WASP-12b is. WASP-12b is in an orbit so tight that its mass loss rate is about 1,000 times higher, and its orbital decay, as we have seen, is rapid enough that the planet has only a few million years left before it is consumed. HD 189733b is in a much more comfortable orbit. The mass loss is real, the orbital decay is probably present at some level, but the timescale for total atmospheric loss is much longer. By the best estimates, HD 189733b has perhaps several billion years left. It is dying, but slowly. It will probably survive its star in some form until the star itself starts to evolve off the main sequence, at which point a different and slower kind of death will take over. The picture, if you put it all together, is of a planet that is in a precarious but not immediately doomed orbit, with a permanent atmospheric circulation, a permanent silicate cloud system, a permanent equatorial jet, a permanent atmospheric leak, and a permanent dull glow from its own thermal emission, all of which have been ongoing for billions of years and will continue, in roughly their current form, for billions more. That is the kind of stability that is, in any human sense, almost impossible to imagine. We live on Earth in an atmosphere that changes daily. The wind shifts, the clouds move, the temperature varies, the seasons turn. On HD 189733b, the wind has been blowing in the same direction at roughly the same speed for longer than the entire history of multicellular life on Earth. The clouds have been making the same kinds of glass droplets in the same parts of the atmosphere for the same stretch of time. The planet, in this sense, is not dynamic. The planet is static. Its weather is, paradoxically, the most permanent feature of the system. Part 9. The first weather map. The Knudsen weather map of HD 189733b from 2007 deserves a longer pause than I gave it earlier because the technique that produced it has gone on to become one of the central tools of exoplanet atmospheric science. The basic idea is simple. As the planet orbits its star, it presents different sides of itself to Earth. When the planet is in front of the star, we see only the night side, because the day side is facing the star. When the planet is behind the star, we see only the day side, because the day side is facing us, but the planet itself is hidden by the star, so we see nothing. In between, the planet shows us a mix of day and night. By watching the system in the infrared, where the planet's thermal emission is strong relative to the stars, you can measure how much light the planet is contributing at each phase of its orbit. Plotting that contribution as a function of orbital phase gives you, in effect, a map of the planet's brightness around its equator. Knudsen's team used the Spitzer Space Telescope to observe HD 189733b for 33 hours of continuous observation, covering the full range of orbital phases. The brightness curve they extracted showed a clear pattern. The brightest point was offset from the substellar point by about 30 degrees in the direction of the wind. The hot spot was not where the star was directly overhead. It was slightly downwind. That displacement was the evidence for the circulation pattern that subsequent models would refine. Since then, weather maps have been made of about 20 other hot Jupiters with various degrees of detail. The technique has been refined. The instruments have improved. The James Webb Space Telescope, which we have already met in our previous story about K2-18b, can now do versions of this measurement at higher precision and at wavelengths that Spitzer could not reach. But HD 189733b was the first. The Knudsen map, for the rest of the field's history, will be the first weather map of an exoplanet. It is one of the small founding documents of a discipline that, in 2007, did not yet exist. Here is the thing I find most beautiful about that result, which is easy to miss when you read the original paper. The planet they were mapping is a hot Jupiter, 64 light-years from Earth in the constellation Vulpecula. The technique they used relied on a 33-hour continuous observation by an infrared space telescope. The data was processed on computers in Pasadena, California. The resulting map was published in a journal that was, by then, available to anybody on the internet for the price of a subscription. From the moment Knudsen hit submit on the manuscript, every weather forecaster, every meteorologist, every atmospheric chemist, every climate modeler in the world had access to a weather map of an alien world. That is, in a quietly profound sense, an extension of what humans have always done. We have been mapping weather on this planet for centuries. The first weather maps by people like Edmund Halley in the late 1600s and Heinrich Brandes in the early 1800s were maps of Earth. Then we mapped the weather of Mars with the Viking landers in the 1970s, then Venus with the Venera probes, then Jupiter and Saturn with Voyager and Galileo and Cassini, then, finally, in 2007, the first planet around another star. The expansion of weather mapping over 400 years has gone from one planet to dozens. HD 189733b was the first that was not in our own solar system. It will not be the last. There is a small but important detail about how the Knudsen result was processed. That is worth mentioning. The data, when it came down from Spitzer, did not arrive in the form of a finished weather map. It arrived in the form of a brightness curve, a long string of numbers showing how the system's infrared brightness varied over 33 hours of observation. To turn that curve into a map, the team had to invert the data. They had to assume a model of the planet's surface brightness as a function of longitude, fit the model to the observed curve, and extract the parameters. The inversion was, in the language of the field, an inverse problem. Inverse problems are notoriously difficult. The same observed curve could, in principle, be produced by many different surface brightness distributions, and choosing the right one requires care. The team handled this by using a regularized inversion, which means they imposed certain reasonable assumptions like that the brightness should vary smoothly across the planet's surface and let those assumptions guide the fit. The result was a map, but a map with uncertainties. The hotspot was, by their analysis, offset from the substellar point by 30 degrees plus or minus several degrees. The temperature contrast between day and night was, by their analysis, roughly 500 degrees Celsius, again with uncertainty. The map was not, in any sense, a photograph. It was a statistical reconstruction. But it was a reconstruction that, for the first time, gave a picture of weather on a planet that nobody had ever seen up close. Subsequent observations with better instruments and longer integration times have refined the Knudsen result considerably. The hot spot offset has been measured more precisely. The day-night temperature contrast has been better constrained. The vertical structure of the atmosphere has been probed with multi-wavelength observations. By the time of this telling, the picture of HD 189733b's atmosphere is far more detailed than what was available in 2007, but the basic shape of an eastward displaced hotspot driven by an equatorial jet has held up. The first map was, in its broad strokes, correct. Part 10. What HD 189733b shares with WASP-12b. If you have been paying close attention, you may have noticed that HD 189733b shares a number of features with WASP-12b, the planet in our previous story. They are both hot Jupiters. They both orbit close to their stars. They both have day-side temperatures of around 1,000 to 2,000 degrees Celsius. They both have thick hydrogen-helium atmospheres. They both have measurable atmospheric mass loss. They are both, in some sense, dying. The differences are what make them interesting in different ways. WASP-12b is in a much tighter orbit, at the edge of being torn apart by tidal forces, with a measurable orbital decay rate that gives it only about 3 million years before it is consumed. HD 189733b is in a more comfortable orbit, losing atmosphere more slowly, with a remaining lifetime measured in billions rather than millions of years. WASP-12b is at the catastrophic end of the hot Jupiter spectrum. HD 189733b is at the long, slow, persistent end. Both are real, both are common, both are part of the same family of objects. The hot Jupiter family, taken as a whole, is one of the more peculiar discoveries of modern astronomy. Hot Jupiters are giant planets that orbit very close to their stars, in orbits ranging from about 1 day to about 10 days, with masses ranging from about half of Jupiter's to several times Jupiter's. They were among the first exoplanets ever discovered because their large size and short orbital periods make them the easiest planets to detect by the radial velocity and transit methods. By 2015, more than 1,000 had been catalogued. By the time of this telling, the number is several thousand. What is interesting about hot Jupiters as a population, beyond their individual quirks, is the way they have shaped our understanding of how planetary systems form. For most of the 20th century, planet formation theory was built around the example of our own solar system, in which giant planets like Jupiter and Saturn are in wide outer orbits, far from the Sun, where ices can condense and provide the seed material for giant planet cores. The discovery of hot Jupiters in the 1990s was a direct contradiction of that picture. Giant planets, it turned out, do not always sit in the outer parts of their systems. Some of them are inside the inner solar system, in orbits closer to their star than Mercury is to ours. The standard picture had to be revised. The revision, when it came, introduced the concept of planetary migration, and that concept has since become a central part of the theory. There is a thought experiment worth doing, which is to ask what an inhabitant of HD 189733b's atmospheric layer might experience, if such an inhabitant could exist. The answer, almost certainly, is that no such inhabitant can exist. The temperature is too high for any organic chemistry we understand. The pressure is too variable. The wind is too constant. There is no surface for any organism to adhere to. There is no liquid water anywhere in the atmosphere because the temperature is far too high for water to be liquid. There is no obvious source of metabolic energy gradients of the kind that life on Earth uses. Every possible life-supporting feature, when you go through the list, is absent. But the thought experiment is still useful because it tells us something about what habitability actually requires. Habitability is not a single threshold. It is a long list of co-occurring features that, on Earth, all happen to be present at once. Liquid water, a solid surface, a moderate temperature range, a protective atmosphere with the right composition, a stable star that does not flare too violently, a magnetic field, a long enough timescale for chemistry to do its slow work. HD 189733b has none of these, WASP-12b has none of these, most hot Jupiters have none of these. The galaxy is full of beautiful, dramatic, well-characterized exoplanet atmospheres that are, by every available measure, completely uninhabitable. That is, in a sense, useful information. We are learning by characterizing worlds like HD 189733b what kinds of conditions do not produce habitable environments. The negative results are part of the picture. We know now that hot Jupiters are not habitable. We know that worlds with permanent supersonic winds and silicate cloud layers are not the kind of places where life is going to take root. We know that the search for habitable worlds, when it succeeds, will succeed somewhere else, around different kinds of stars, on different kinds of planets. The hot Jupiter catalogue is teaching us, very concretely, where not to look. That, by itself, is one of the contributions of HD 189733b to the broader enterprise of astrobiology. The planet is not habitable. We know this with high confidence. We know it because we have characterized the atmosphere in extraordinary detail. We know what the chemistry is. We know what the temperature is. We know what the wind speed is. We know what the cloud composition is. The planet, in the catalogue of where life might be, is in the column marked No. That is, from the standpoint of narrowing the search, useful. What is peculiar about hot Jupiters, when you think about it, is that they should not, by any simple model, exist. The standard picture of how planetary systems form, developed over the second half of the 20th century, is that planets form in a disk of gas and dust around a young star. And that giant, planets like Jupiter form specifically in the cooler outer regions of the disk, where ices can condense into solid grains and grow into massive cores. By that picture, you should not expect to find Jupiter-mass planets in two-day orbits, very close to their stars, where the temperatures during formation would have been too high for ices to condense. The discovery of the first hot Jupiter, 51 Pegasi b, by Mayer and Queloz in 1995 was a profound surprise to the field. The resolution of the puzzle, which took the better part of a decade to work out, is that hot Jupiters do not form where they are now. They form, like Jupiter itself, in the outer parts of their parent disks. They then migrate inward over millions of years by gravitational interaction with the disk, with other planets, or with binary stellar companions. By the time the disk dissipates and the system stabilizes, the giant planet is in a tight orbit close to its star, in a place it could never have formed in the first place. The migration story, when it was worked out, became one of the central narratives of modern planet formation theory. Doug Lynn and Peter Bodenheimer at the University of California, Santa Cruz, and Derek Richardson, then at the University of Toronto, did the foundational work in the 1990s. What this means for our story is that HD 189733b and WASP 12b are not where they were born. Both of them, billions of years ago, formed in the outer parts of their stars' protoplanetary disks, perhaps several astronomical units from the star where ices could condense and the chemistry was right for giant planets to grow. Both of them somehow ended up in tight, close-in orbits, where they have been ever since, evolving according to the slow physics of tidal interaction and atmospheric stripping. WASP-12b in its final phase will be consumed. HD 189733b, more probably, will simply persist for a very long time, slowly losing atmosphere, slowly shifting orbits, slowly drifting into the long, stable middle age that hot Jupiters seem to settle into when they are not in immediate danger of being eaten. Part 11. What it would be like if you could be there. Here is a thought experiment that I sometimes do when I read about HD 189733b, which is to imagine what it would be like to be there. Not in any practical sense. The planet is 64 light-years away, which would be at least a several thousand-year journey for any spacecraft we know how to build, and the planet has no surface to land on, and the upper atmosphere, where you might hover in some hypothetical balloon, is hotter than any structural material we currently know how to make. The thought experiment is not about engineering. It is about what the experience of the place would be if we could somehow set the engineering aside. You arrive in the upper atmosphere somewhere on the day side, near the silicate cloud layer. The sky around you is, in every direction, a deep cobalt-blue. The blue is not, as on Earth, a colour painted on a celestial dome. It is a colour suspended in the air around you. The air is full of tiny droplets of liquid silicate, smaller than the wavelength of light, scattering blue light back at your eye from every angle. There is no horizon in the way Earth has a horizon, because there is no surface. The blue extends down indefinitely into the lower atmosphere, where it gradually gets darker and hotter and denser, until somewhere far below you the gas becomes so compressed that it transitions into a strange supercritical fluid that has no equivalent in our own world. Above you, the star, HD 189733, is much smaller and much redder than our own Sun looks from Earth. It is a K-type star, slightly cooler than the Sun, and the planet is so close to it that the star's apparent diameter is more than 20 times what the Sun looks like from Earth. You would not be able to look at it directly without being blinded. The light from the star is not, importantly, white. It is yellowish-orange, the colour of an incandescent bulb. The blue sky around you is the planet's own scattered light against that yellow-orange illumination. The wind is the dominant feature of the experience. You are not standing still. You are being carried at the speed of 7 times sound in a permanent eastward direction, across the sky of the planet, by the equatorial jet. The wind is not, importantly, gusting. It is steady. It does not shift. It does not pause. It is the same wind blowing the same way, at the same speed that has been blowing here for the entire age of the system. If you stayed in this layer of the atmosphere for long enough, the wind would carry you all the way around the planet, from the day side to the night side and back to the day side, in a few hours. The clouds, from your position, are not visible as discrete objects, because they are made of droplets too small to see. You are inside a cloud in the same way that on Earth you are inside the air. The cloud is, however, very real. It is condensing slightly cooler than your immediate altitude, falling slowly under the planet's gravity, evaporating again as it descends into hotter regions, rising as vapor, condensing again. The whole cycle is happening continuously, at every altitude, at every part of the planet, all the time. You are inside a permanent atmospheric storm of liquid glass. The night side, if the wind carries you that far, is much darker. The thermal emission of the planet is reduced because the temperature is lower and there is no starlight at all. The atmosphere itself around you no longer glows. The cobalt-blue, which on the day side dominates everything you can see, fades into a deep slate grey, and then into something approaching darkness. There is no horizon to look toward because there is no surface. The night side of HD 189733b is a strange kind of darkness in which the planet's own thermal glow, dim but not absent, is the main source of light. You can, if you wait long enough, see by it. You can see the wind. You can see the clouds. You can see, in your immediate vicinity, the falling glass. The clouds, on the night side, are denser and lower because the temperature is more conducive to condensation. There may, on the night side, be patches where the cloud droplets fall faster than the wind can carry them sideways, and where the falling becomes, for stretches of the atmosphere, the dominant motion. This is where, in the most literal sense, it rains glass. The droplets fall slowly in the planet's gravity downward through the atmosphere until they reach altitudes where the temperature is high enough to vaporize them again. The rain, in this picture, is real. The rain is also, on its way down, being blown sideways at 1,000 kilometers an hour. The rain falls, but it falls at a very small angle to horizontal, almost flat, across the sky. It is worth stopping to picture this carefully, because it is genuinely unlike any rain that has ever fallen on Earth. On Earth, rain is a vertical phenomenon. Drops fall more or less straight down, with a small lateral drift from the wind. On HD 189733b, the lateral component dominates by a factor of more than 100. If you imagine a single droplet, condensed in the upper atmosphere, beginning its fall under the planet's gravity, the droplet's downward velocity, by the time it reaches the lower cloud layers, might be a few meters per second. Its sideways velocity, the speed of the wind, is more than 2,000 meters per second. The trajectory is almost flat. The droplet is, in effect, being thrown horizontally with a tiny vertical component and is travelling vast distances around the planet for every meter it descends. That image, when you sit with it, is one of the more peculiar visual realities of modern astronomy. We talk about rain casually, as if rain is a single phenomenon. The rain on HD 189733b is, technically, rain. It satisfies the meteorological definition: droplets condense from vapour, fall under gravity, eventually reach a layer where they evaporate again. But it does not look, in any sense, like Earth rain. It looks like a horizontal stream of glass particles moving so fast that the falling motion is almost imperceptible. In a permanent atmospheric current that has been doing this for billions of years. That is, in some sense, the actual experience of HD 189733b. A wind that does not stop, a sky that is blue everywhere, a rain of liquid glass falling at a flat angle in the dark on the night side, perpetually. A star you cannot look at, sitting at the same place in the sky day after day, year after year, age after age. No surface, no horizon, no silence, just weather, all the way down. The strangeness of this kind of place, when you sit with it, is hard to fit into ordinary language. We do not have, in any human language, the right vocabulary for permanent weather. We have words for storms, which start and end. We have words for seasons, which come and go. We have words for climate, which describes long-term patterns but still implies variation. None of those words quite captures what is happening on HD 189733b, which is a single, continuous, uninterrupted atmospheric event that has been going on for billions of years and will continue, with very little change, for billions more. The closest analogue I can think of in human experience is something like the Great Red Spot on Jupiter, which has been an active storm for at least 350 years since it was first observed. But Jupiter's red spot is a single feature, embedded in a larger atmosphere that is otherwise constantly varying. HD 189733b's wind is the entire atmosphere. There is no part of it that is varying on any scale we can measure. The whole planet, in some real sense, is one storm. There is a thought experiment that I sometimes do, which is to imagine somebody or something that lives long enough to perceive HD 189733b's weather as weather, not a human who lives for less than 100 years and would experience the wind as a single uniform feature of the environment, something whose lifespan is measured in millions of years. Such a being, if you can imagine one, would still not see HD 189733b as varying. The whole evolution of HD 189733b's atmosphere, from the planet's birth to its eventual death billions of years from now, is shorter than the time span over which any meaningful weather change happens. The wind, on the time scale of the kinds of beings that could perceive it, is fundamentally constant. There is no variation to perceive. The planet is the wind. Part 12. What this teaches us about exoplanet atmospheres in general. HD 189733b, as I mentioned earlier, is the most carefully studied exoplanet in the catalogue. The reason for that is its proximity and its brightness and its repeatability, and the fact that almost every technique anyone has invented for studying an exoplanet's atmosphere has been tried on this one before being applied elsewhere. As a result, almost everything we know in general about the atmospheres of close-in giant planets has been informed in some way by what we have learned about HD 189733b. We know that hot Jupiters tend to have in their upper atmospheres water, methane, carbon monoxide, sodium, potassium, and various other species in proportions that depend on temperature. We know that, at certain temperature ranges, silicate clouds form and dominate the optical appearance of the planet. We know that at other temperature ranges, different cloud species form, including iron-bearing clouds and titanium-bearing clouds, which can give different planets their own distinctive colors. We know that the wind patterns are dominated by the day-night temperature gradient modified by the rotation of the planet, with eastward equatorial jets being the most common pattern. We know that some fraction of the upper atmosphere is being lost to space at all times, with the rate depending on the proximity of the planet to its star and on the strength of the star's ultraviolet flux. All of these general findings have been refined and extended by observations of other planets. WASP-12b, with its egg shape and orbital decay, contributed insights about the extreme limit of hot Jupiter behavior. K2-18b, in our previous story about a planet possibly hosting biosignatures, contributed insights about Hesian worlds and about how the smallest detection might still be the most significant. The TRAPPIST-1 system, with its 7 small planets in tight orbits around a red dwarf, has contributed insights about the atmospheres of small, temperate worlds. Each new system adds something to the picture. The picture, taken as a whole, is now rich in a way that, 25 years ago, it was not. Here is the part I think is most quietly remarkable. We have, in the past 25 years, gone from knowing the atmosphere of one planet outside our solar system to knowing the atmospheres of dozens in detail, with chemistry and weather and circulation patterns and even mapped hotspots. The expansion is not slowing down. Every new generation of telescopes, including the upcoming European aerial mission, the ground-based extremely large telescope, and the proposed Habitable Worlds Observatory, will add many more atmospheres to the catalogue. By the time today's children are entering middle age, the atmospheric chemistry of perhaps 1,000 exoplanets will be at least partially characterized. The catalogue of weather in the galaxy will be a large catalogue. HD 189733b will, in that future catalogue, be one of the early classics, the first to have its colour measured, the first to have its weather mapped, the first to have its wind speed clocked, the reference object against which subsequent measurements were calibrated. Not necessarily the most famous, in popular terms, not necessarily the most photogenic, but the one in the technical literature that future astronomers will keep coming back to. There is a parallel in the history of science with the way other reference objects have functioned. In stellar astronomy, certain bright stars like Vega and Sirius and Arcturus became reference points for spectroscopy, photometry, and parallax in the 19th and 20th centuries. The properties of those stars were measured first and most carefully, and subsequent measurements of other stars were calibrated against them. The stars themselves were not chosen for any astrophysical importance. They were chosen because they were bright and convenient. The same dynamic applies in a smaller way to exoplanets. HD 189733b is not particularly important by any objective measure. There are larger hot Jupiters, hotter hot Jupiters, more dramatic hot Jupiters. But it is bright and convenient and well characterized, and so it has become, by accident of geometry, one of the reference points for the field. The history of any scientific catalogue is, in some sense, the history of a few unusually convenient objects becoming famous. The convenient ones get studied, the studied ones become well understood, the well understood ones become the calibration standards. The standards stay in use, sometimes for decades or centuries, even after better targets have been identified. HD 189733b in the catalogue of exoplanet atmospheres is one of those convenient objects. It will probably remain in the literature, in the textbooks, in the standard examples for as long as there is exoplanet atmospheric science. It earned its place by being well positioned. Its scientific value in the future of the field will be much larger than its astrophysical uniqueness would have suggested. Part 13. 64 light-years. There is something about the proximity of HD 189733b that I want to spend a moment on because it changes the texture of the story in a way that is not always obvious. 64 light-years by cosmic standards is close. It is roughly 2,000 times closer than the center of our own galaxy. It is roughly 10,000 times closer than the Andromeda galaxy. It is, on the scale of the universe, very nearly nothing. The light reaching Earth from HD 189733 tonight left that star in the late 1950s or early 1960s. That is within living memory of many people listening to this. The light that the Discovery instruments observed when Bushi's team measured the radial velocity wobble in 2005 left HD 189733 around the year 1941. Anybody alive in 1941 was alive when the photons that confirmed this planet 6 decades later started their journey toward us. That short timescale matters because on the scale of stellar lifetimes, it is essentially nothing. The planet has been doing what it is doing tonight at 5,400 miles per hour for billions of years. The fact that we are now able for the first time in human history to read the spectrum of its weather with the level of detail that we can is a function of having instruments that did not exist 65 years ago. The light that those instruments are reading 65 years ago was on its way. The information was in transit. It just had no destination yet. This is in many ways the deepest pattern of modern astronomy. The information has been arriving on Earth for as long as there has been an Earth. The chemistry of HD 189733b's atmosphere has been written into the spectrum of its star every transit, every 2¼ days since the planet formed. The information was always arriving, we just did not have the instruments to read it. Now, in our generation, we have the instruments. The reading is, in human time, brand new. 64 light-years also means that, in principle, communication with anything on HD 189733b would be possible on a human timescale. If there was somebody on the planet who wanted to talk to us, and we wanted to talk back, the round-trip time for a radio message would be 128 years. Long, but not impossibly long, comparable to the time between the building of the Brooklyn Bridge and now. A great-grandparent could send a message, a great-grandchild could receive a reply. There is a thought that I find genuinely useful when I sit with the proximity of HD 189733b. 64 years ago, in the early 1960s, the photons that are arriving on Earth tonight, with their tiny atmospheric chemistry encoded in them, started their journey. The world they left, here on Earth, was a world without exoplanet astronomy, without space-based telescopes, without the kind of high-precision spectrographs that would, by 2015, be able to detect a 5,000-mile-per-hour wind on a planet 64 light-years away. The whole field that now reads those photons did not yet exist. The instruments did not yet exist. The mathematical techniques did not yet exist. The discipline, as a discipline, did not yet exist. The photons travelled at the speed of light through empty space for 64 years, while the human race built up, on Earth, the capability to read them. That is, in some sense, a story about the slow nature of preparation. The information was always coming. The instruments were always being built. The two timelines, the photons travelling and the technology being developed, happened to converge in our generation at the moment when the photons were arriving and the instruments were ready. By coincidence, almost, the two were synchronized. 64 years of light travel matched, very approximately, the time it took human beings to develop the technology required to read the message at the other end. That kind of synchronization is, I think, one of the most quietly remarkable features of modern astronomy. The light from many of the objects we now study has been traveling for centuries or millennia or millions of years. The technology required to read what that light is carrying has been developed in a tiny fraction of those time spans. We are, in some sense, the first generation of human beings for whom the cosmic mail has been delivered to a properly working postal system. The previous generations did not have the inboxes. The mail was still arriving. They could not open it. There is, of course, no one on HD 189733b. There can be no one. The planet is a 1,000-degree gas giant with no surface and a permanent global wind of glass, particles. Nothing on it could be alive in any sense that any organism we know about could be alive. I am not saying that life is impossible on hot Jupiters. I am not saying that the chemistry we know is the only chemistry that exists. I am not saying that future biologists working on exotic possibilities will not eventually identify some hypothetical metabolism that could, in principle, function in an environment like the upper atmosphere of HD 189733b. What I am saying is something quieter than that. What I am saying is that, by every standard of what we mean by life on Earth, by every chemistry we have ever observed in any laboratory, by every metabolism we have ever catalogued in any organism, this planet is not a place where life could begin or be sustained. The temperature gradient is wrong, the pressure is wrong, the chemistry is wrong, the composition is wrong. The wind, by itself, would tear apart any cellular structure faster than any cell could form. The planet, in the catalogue of habitability, is in the column marked No, and the No is unambiguous. The communication thought experiment is, in this case, purely hypothetical. But the proximity matters anyway because it tells you something about what is in reach. HD 189733b is in our neighbourhood. We can study it in detail with the instruments we have now and with the instruments we will have in the next few decades. The pictures we are putting together of its atmosphere will, in the next 20 years, get sharper. The wind speed estimate will be refined, the cloud chemistry will be confirmed. The atmospheric loss rate will be tightened. The weather map, by the late 2030s, will be a much more detailed weather map than the one Knudsen made in 2007. We are, in some sense, 100 years ahead of the much later cosmologists who will come along in their distant centuries and study HD 189733b. With whatever instruments they have, they will know more than we do. They will, with luck, look back at the early papers, the Bucci discovery, the Tinetti water detection, the Knudsen weather map, the Louden and Wheatley wind measurement, the Evans colour determination, and they will see them as the foundational documents of the field. The first chapter, the chapter our generation wrote, Part 14, Coming Home. We did not set out to find a world made of cobalt-blue weather. We set out to find planets at all. The early radial velocity surveys in the 1990s were looking for any planets of any kind around any nearby stars. The discovery of 51 Pegasi b in 1995 opened the door. The next decade, the wide field transit surveys looked for any planets that happened to pass in front of their stars from our point of view. HD 189733b was one of the early finds in that effort. Nobody, in 2005, when the planet was first announced, expected that it would turn out to be the most carefully studied exoplanet in history. The atmosphere, the colour, the wind, the rain, the weather map, the leaking were all later discoveries. They came one paper at a time over 20 years from teams scattered across the world. That is the temperament of this kind of work. The discoveries do not come from a master plan. They come from a slow accumulation of careful measurements by many different groups over a span of years, until at some point when you stand back, you notice that the picture has filled in. HD 189733b was, in 2005, just another hot Jupiter. By 2015, it was the textbook example of what a hot Jupiter atmosphere looks like. By the time of this telling, it is one of the most thoroughly characterized objects in the entire exoplanet catalogue. The accumulation happened by inches. It happened the way most important things in science happen, slowly, by many hands, with nobody in charge of the larger pattern. What we know now is enough to fill out a long evening like this one. The planet is a gas giant 64 light-years from Earth in the constellation Vulpecula. It orbits its star in 2¼ days. Its day side is 1200 degrees Celsius. Its sky is cobalt-blue from horizon to horizon, with no horizon. Its atmosphere contains water, methane, sodium, potassium, carbon monoxide, hydrogen, helium, and tiny droplets of liquid silicate. Its wind blows from the day side to the night side at 5,400 miles per hour in a permanent equatorial jet that has been going on for billions of years. Its atmosphere is slowly leaking into space. Its rain on the night side is droplets of glass falling almost flat across the sky at speeds that no terrestrial weather has ever come close to. The whole picture, taken together, is one of the more peculiar weather systems we have ever measured. You can let the picture rest for tonight. The wind is still blowing on HD 189733b. The clouds are still drifting. The rain, on the night side, is still falling, in its sideways way, in its glass droplet way, in its silent way. None of it depends on whether you are awake to hear about it. None of it depends on whether anybody on any planet in any galaxy is paying attention. The weather is just there. The wind is just there. The atmosphere, in its slow, patient circulation, is doing what hot Jupiter atmospheres have been doing for as long as there have been hot Jupiters. There is, I think, a particular kind of peace in knowing that. The wind on HD 189733b will not stop tonight because of anything happening on Earth. The wind will not start blowing harder or slow down or change direction because of any human concern. The wind is on its own clock. The clock is, by every measurement we have ever taken of it, set to a setting that has not changed in billions of years and will not change in billions more. You can, without any sense of being inattentive, let it go. That kind of permanence, when you sit with it, is one of the gifts of cosmic scale phenomena. Most of what we worry about in an ordinary day is on a time scale that responds to what we do. Our work shifts based on our effort. Our relationships shift based on our attention. Our health shifts based on our choices. There is, in almost every domain of ordinary life, a feedback loop in which what we do affects what happens. That feedback loop, while it makes us effective, also makes us tired, because we cannot ever quite step out of it. Everything, almost always, depends on us. The wind on HD 189733b does not depend on us. It does not depend on anything we do, anything we say, anything we think, anything we fail to do. It is, in the most absolute sense, None of our business. The star is going to keep heating the day side. The temperature gradient is going to keep driving the wind. The wind is going to keep carrying the silicate droplets sideways at the speed of 7 times sound around the equator of the planet for billions of years. None of it is on our schedule. None of it is on our list. None of it requires our input. That release, when you can feel it, is one of the better experiences modern science offers. The observable universe is, on its own scale, doing things that have nothing to do with us. We can watch, we can measure, we can describe, we cannot interfere. The non-interference is not a limitation, it is a feature. It means that, for the duration of an evening like this one, you can put down the everyday weight of feeling responsible for everything that is happening and just listen to the story of weather on a faraway planet without it being a problem you have to solve. The constellation Vulpecula is in the summer sky in the northern hemisphere, near the bright star Altair. It is a small, dim, modern constellation drawn by the Polish astronomer Johannes Hevelius in the 17th century and depicting a small fox holding a goose. Hevelius lived in the city of Gdansk, then called Danzig, and ran one of the best private observatories in Europe. His wife, Elizabeth Hevelius, who continued his work after his death, was one of the first women known to have done serious, original astronomy in early modern Europe. Her catalogue revisions, published posthumously, included refinements of many of his original positions, including some of the stars in Vulpecula. He invented or named 11 new constellations to fill in the gaps between the older Greek and Roman patterns. Vulpecula was one of his. The original Latin name was Vulpecula cum ansere, the little fox with the goose. The goose has, in subsequent centuries, mostly been dropped from the name, but the fox remains. The fact that we now know there is in this small, dim, almost forgotten constellation a hot Jupiter with a permanent supersonic wind of liquid glass is the kind of thing Hevelius would have found startling. He died in 1687. He spent most of his career making detailed catalogues of stars with positions accurate to a few arc-minutes by eye without a telescope. The idea that, 340 years later, somebody would point a different kind of telescope at one of his catalogue stars and measure the wind speed in the upper atmosphere of a planet around it in real time would have been, to him, science fiction. He would have loved it. He would have found it consistent with his own way of thinking, which was that careful observation of the heavens, sustained over generations, eventually yields knowledge that no individual observer could have predicted. It is not a striking pattern. Most people who look at the summer sky have never noticed it. HD 189733 is one of its many faint stars just below the threshold of unaided eye visibility, sitting in its catalogue position at right ascension, 20 hours and 43 minutes, and declination plus 22 degrees and a half. But the star is there, and around it, every 2¼ days, a cobalt-blue gas giant the size of Jupiter is making a fast lap of its star, with its atmosphere full of glass, with its wind blowing sideways across the day side at 7 times the speed of sound, with its rain falling almost flat in the dark of the night side, with its atmosphere slowly drifting away in a process that will continue for billions of years more on a clock that is much longer than any of ours. There is one more thought I want to leave you with before we let the planet go for tonight. The light from HD 189733 that has been used in every measurement of its planet's atmosphere over the past 20 years is light that left the star on average 64 years ago. The light arriving on Earth tonight that some future paper will use to refine the wind speed measurement left the star 64 years ago. The information is always slightly out of date. We are always, in this kind of work, looking at history. The wind speed we measure tonight is the wind speed of HD 189733b in the early 1960s. The chemistry we measure tonight is the chemistry of the early 1960s. The colour we measure tonight is the colour of the early 1960s. None of it is, strictly speaking, the planet today. The planet today, on its own clock, is doing whatever it is doing 64 light-years away, and we will not see what it is doing now until 64 years from now, when those photons arrive. The lag does not matter in any practical sense because the planet's atmosphere is essentially unchanged on the timescale of human history. The wind 64 years ago was, almost certainly, the same wind that is blowing tonight. The clouds were the same, the chemistry was the same. The planet, on this timescale, is fixed, but the lag is real, philosophically. We are watching a delayed feed. The studio is, in some sense, 64 light-years away, and the broadcast is always, by definition, 64 years stale. That is a feature of all astronomy, not just exoplanet astronomy. The light from the Andromeda galaxy that you see in your binoculars on a dark night is 2.5 million years old. The light from quasars in the deep universe is billions of years old. We are always, when we look up at anything beyond our own atmosphere, looking back in time by amounts that depend on how far away the source is. HD 189733b at 64 years is essentially current by these standards, but it is, technically, history. You can let the planet go for tonight. The wind has been blowing on HD 189733b in roughly the same way for billions of years. 64 years of lag is, on that scale, irrelevant. The story we have been telling is, for all practical purposes, the story of what is happening right now. The wind is still blowing. The clouds are still drifting. The rain, on the night side, is still falling. The star is still heating the day side. The atmosphere is still very slowly leaking. The whole permanent system is still doing what it has been doing for as long as the planet has been there. Good night. Sleep well. The wind on HD 189733b is still blowing. The glass on the night side is still falling. The story is tonight exactly where we left it. The fox in the small dim constellation is still doing what foxes in old constellations do, which is sitting quietly in its corner of the night sky. The star, around which our planet of glass weather is orbiting, is still in its catalogue position. The information continues to arrive on Earth every 2.25 days, with each new transit, in the form of slightly modified starlight, which any sensitive instrument that happens to be pointing in the right direction will record. The recording is not happening for our benefit. The recording is just happening the way it has been happening for 64 years before this, the way it will continue to happen long after this evening is over. You can rest, with the eyes of the universe still doing their slow, patient work in the background. The wind on HD 189733b is still blowing. It will keep blowing while you sleep. It will keep blowing tomorrow. It will keep blowing for billions of years. Nothing about it requires your attention. Good night, again. Sleep gently. The glass keeps falling. The wind keeps blowing. The fox, in the small dim constellation, holds its goose in the position Hevelius drew it 340 years ago. The planet that nobody knew was there is still doing what it was always doing. The story is old. The reading is new. The night for tonight is yours.